Welcome to Infinite Hobby Loop. We're starting a new series on the Beige Beauty, a 486SX PC that I picked up off eBay. I'd like to restore it, tear it down, see what makes it tick, and do some upgrades. And with a little luck, it might even play Duke Nukem 3D. Isn't it beautiful? Well, here it is on the bench. I'm about to start tearing into this. If you look at the system the way it is right now, and this is the way it came from eBay. It has a single graphics card in there, and the rest of these I/O ports are on the motherboard itself. Not a whole lot to it. It's got a 3.5-inch floppy drive on the front, and that's about it. So I'm gonna dig in, take this board out because it is BIOS password protected, and I can't see any markings on it anywhere that say what the where the CMOS reset is. So I'm gonna try that and see, take it out, see if I can identify what it is, and go from there. All right, here's that same system. Now we have all of the cables removed from the motherboard itself. It is ready to take out. You can see it a little bit better now, definitely. All those ribbon cables take up a ton of space inside the case. So, a couple of screws up there to take out. One down there. Looks like the board will slide right off. The board is completely loose, but it won't come out this way, and it is supposed to go up and down. If I flip the machine over, you can see that the board is moving freely, but the standoffs never go far enough in to be able to find enough room for clearance. Well, I thought about it a little bit more, and since they can't slide this way, it had to get in there somehow, and taking the plastic and pinching it is not easy. But so I looked at it, and they've got these screws right here on both sides, and I think all I need to do is undo those screws, and this whole thing will flop down because it is in a motherboard tray, which I gotta say I haven't seen in this era of computer before, so wasn't looking for it. All right, and there we go. That did it. So here are all of the parts. Well, the Leatherman isn't, but here are the rest of all the parts that are from the system. So now that I've got a pile of stuff, I'm going to try to get it up and going on the bench here as well. One other thing I noticed while taking this apart is it had a sticker that was covering the CPU and taped to the chassis. If you look at it, it says September 20th, 1994. Well, kind of can't tell, but it looked like it split right on 4. But anyway, September 20th, 1994. So yeah, I love it when there's little dates inside of these old computers. Okay, I've got a keyboard hooked up. This is my ancient Logitech keyboard, but it's not so ancient that it has what it needs. This is actually a PS2 keyboard, so I found this at Micro Center. It's a PS2 to AT style, XT style? AT or XT style adapter. I've got my power hooked up to the power supply that was in the system. Remember when you put these on, blacks go together, so all your ground wires are together in the middle of that. So little tip. And I've got the video card back in, which we'll look at the specs of in a little bit. And I hooked up a dirty, like really dirty, flat panel VGA capable monitor. So this is about time. So here we go. Let's see what happens. That's a good sign. I hear the fan running, at least in the power supply. And there it goes. 46SX, 33 megahertz, 4 megs of RAM. And I'm going to hit the delete key, see if it goes into the BIOS. And enter password. All right, so now I'm at the part where I need to figure out how the hell to get rid of this password. I'm going to look around and see if I can figure out where any type of date code or model code or anything like that is so that I can look it up, because there are a ton of jumpers on this system. And those are obvious, but like these right here, I have no idea what any of these do. So it's going to be tough to set it up without the book, because this is from that era of PC where there were about 1 billion jumpers on the boards. Looking a little closer, there we go. 46 GIOV as in Victor T, and a dock number. So yeah, I lucked out. So this board is made by FIC. and it is the 486 GIO VT. And I found the manuals online, which is awesome. And right here is J7, and J7, oops, sorry about the more. J7 is password clear. So let's clear that password. I did it, I found it. J7 is right there. I couldn't find it by just looking around because it was, the jumper itself was covering up the J7 because it was hanging off like the one next to it. So wait for it. Still wait for, okay. Hit delete. And there we go. We're in. Now to watch it do something, I have hooked up this IDE to compact flash adapter that I have laying around. It's actually out of another project that I have that's a much newer system, but still vintage. Anywho, just hooked up the ribbon cable, and I want to see if I can get it to boot. So let's give it a go. It should auto detect, but let's go ahead and go into the BIOS. See if we can get it to auto detect. Oh, nope. So it detected it like that. I find that hard to believe that it's a 17. It's possible, I suppose. And IDE hard disk drive auto detection. 480 megabytes. It is a 512 megabyte compact flash card. So yeah, I'd buy that. That sounds about right. There are no other drives, so this probably has to air out. Do you accept? No. There we go. Save and exit. It's not going to save, but that's okay. Yep, I'm going to leave that in there because it won't remember that there's no password. F1 to continue. Maybe. Oh, that's looking good. Well, we're gonna have to fix that right away. I just tried to run Duke Nukem and it said not enough memory. That seems like that might be our next priority because no Duke Nukem, that's not gonna work. Well, to get around my battery problem, I whipped this up real quick. I had this coin cell thing and some connectors, so I soldered it up and threw a coin cell that I had in there. And it tests out, I can't hold it and show you, but it tests out with this voltmeter to 2.84 volts. And if you look at the board itself, the board has this battery, which I tried to pry off, so I'll have to desolder that and put a new one in. But this jumper right next to it, let me get a pointer here and show you. This jumper, whoa, that's disorienting. All right, so this jumper that's right here, this J1 path, this is a positive and this is negative. And if you switch this jumper, well, I guess that's a header. If you switch this jumper to the position it's in now, which is J3, in between pins 1 and 2, it will actually use the external battery. If it's between 2 and 3, it uses the internal. So I've got it set for external. I'll plug this in, and that'll at least get us past our CMOS issues until we can get this here battery replaced. And like I said, this just goes on here like this. So I should just be able to press it down, and there we go. All right, I thought I'd run a few benchmarks. We've got 158 megahertz AT using the landmark speed test. It's seeing it as a 486 DX33, and everything seems to, but it is most definitely a 486SX. DX is better, though it's not. So, anywho, this is one of the things that I was thinking I might actually upgrade, is that this board supports a 486 DX2 66, so that'd be a pretty healthy upgrade, and you'd get the FPU. And here it is running with the Cirrus Logic video card. It is significantly slower at 8,777.14 characters per millisecond. And here is the top bench score of a 132. For those of you who are watching closely, this is the Cirrus Logic card that I tried first that was definitely the slower of the two. It doesn't have its RAM slots populated either for more video RAM, but I think that would just, I'm not positive, but I think all that would do in this era of video card would be to give you higher video resolutions, not actually more speed, because it's not like there's actual textures going down to the card or anything like that. So you're not going to get any frame rate improvements. But here is that chip. You can see it's Cirrus Logic, like I said, MVGA, AVGA for VL, Victor L. And then here's that main Cirrus Logic ASIC. And now that I've got it out of the system, even though I didn't want to because it's the faster card, I thought I'd show you this card. It's the S3 Stealth 64 VLB card, manufactured, or at least copyright, 1994. That is it. It too does not have any video RAM chips populated, and it has a jumper on there that I have no idea what it does. I'll show you the back side of this card as well. Ah, yes, VLB goodness. Man, there's one thing I hate about the VLB slots, though. They are hard to press a card into. I feel like I'm going to snap the motherboard in half. So while I've been doing this on the bench here like this, what I'm doing is I'm putting my hand underneath it and holding it in place while I shove that. Gotta watch out for my ring. Shove that card in there. Otherwise, I hear the board flex and crack when I'm putting it in there. It's just terrible. So I don't know if we're missing a standoff or what, but scary stuff. Probably want to put the video card in before I put it back in the case. Went through my bag of RAM chips, and here I have some 30-pin SIMMs. You need 4 of them for a machine like this. We'll talk about that in a second. But you need 4 of them, and this looks like it's 80 nanosecond RAM. The memory that's in the system that I've been using is 70 nanosecond RAM. So we definitely have a speed mismatch, so we're gonna have to slow down the clocks. But it should work, and will get us enough RAM that we can at least play some Duke Nukem. Okay, as promised, here is the presentation that I threw together for the various types of SIMMs that are used on this system. So a little bit about the processor itself. It's an Intel 486, which we talked about. The Intel, actually, this 486 ran from 1989 to 2007. That's how long they actually manufactured it, which is 18 years. I had to do the math. It's 18 years. Later in its life, it was used mostly in notebooks and other embedded systems, but definitely had one heck of a lifetime. The DX model had the integrated floating point unit, or math coprocessor as it's called, to accelerate floating point math, as one does. The SX model, you could indeed buy a 487 SX, and this is the last time I believe that was a possibility. I think starting with the Pentium, they all had an FPU built in. It had 8 kilobytes of internal L1 SRAM cache. We haven't talked about SRAM, but it stands for static RAM. It's a faster type of RAM, as well as lower power. And it did support an external cache, the 46 did. It had the same real and protected modes that the 386DX had, so you could program it in both segmented mode, as in the case of real, or with protected mode, you could actually use 32-bit flat memory addressing internally. The VCC is 5 volts, plus or minus 10%. Some of the later chips, especially the mobile and the embeddeds, were 3.3 volts. Important to note, it came in a DX2 and DX4 varieties. I'm actually going to upgrade this system to a DX2, which is the fastest that this motherboard can handle. But the DX2 runs at twice the external bus clock. And there is a DX4, which won't work in this board, sadly, but the DX4 ran at 3 times the external bus clock. And no, that's not a typo. There was a DX3 that was out for a while as well that ran at 2.5 times the speed. Or actually, I don't think it was ever released. And then also important, it came in, like I said, mobile versions. There was an SL and GX versions that were put out for low power environments. And then there were also enhanced models that were write back cache. And then also note that I'm talking about only the Intel 486 here. There were also third-party manufacturers that made them. Cyrex made them, as did AMD and a handful of other people. Here's a picture of the 486DX processor pinout that I grabbed from the data sheet. It has a 32-bit wide external data and address bus. Here's a bunch of the address pins, and here's a bunch of the data pins. Don't know where they all are, obviously. But it's also important to note that unlike the 386, both the SX and the DX both have the 32-bit bus. The 386 SX, I think it ended up having a 24-bit bus instead of the full 32-bit. So that is a change that they made in this processor. So let's talk about the 486 address bus. So the address bus in a system is responsible for selecting where in the system memory to fetch code and or data, or to write code and or data. The address bus on the 486 is 32 bits wide. That is literally 32 pins externally. It gets a little more complicated because of the block enables, which allows it to work with byte, word, or D word. And it's pretty fancy. It's actually kind of a clever solution to the problem. So if you want to look at that, I recommend just going to look at the data sheet, or if you want me to, I could maybe make a future video on how that works. But, you know, for this presentation, just assume it has 32 bit pins on the address bus. So 32 bits wide, 2 to the 32nd, gives you 4 gigabytes of addressable memory. However, obviously, a DRAM SIMM doesn't go to 4 gigabytes because most systems don't allow 4 gigabytes, including this one. And in fact, most DRAM SIMMs can't go above 24 bits of addressable memory space. And I'll show you why that is right now. So 30-pin SIMM address bus, the way that this works, think of a spreadsheet that has rows and columns like Excel or any other Google Sheets or whatever they're called. So anywho, it's a row column mechanism. So there are 12 address lines that go into, interesting. There are 12 address lines that can go into the SIMM. That's 4096 rows or 4096 columns. So you actually strobe in the row, and then you strobe in the column, and the chip latches and sees both of them. Or this, I shouldn't say chip. The stick latches and sees both of them. And then it knows which cell you are actually accessing. That means that up to 16 megabytes can be addressed on a SIMM. So again, 2 to the 12th times 2 to the 12th, and there's your math, and that gives you 16 megabytes of addressable space. So the fanciness comes in that you can actually address some of these lines to specific slots, and using a chip select scheme, you can actually go above 16 megabytes, as most systems, including this one, obviously allow you to do. So if you want me to show you the digital logic and how the glue logic and the pieces would go together to actually make it select a specific chip, let me know, comment, and I'd be happy to make a video about that. So 72-pin SIMM address bus, the way that they work is almost identical. In fact, you get 24 bits of addressable space with the same row and column strobe, and the same 12 address lines, just like the 30-pin SIMM. The difference is that they also have an additional couple of pins for rank. So rank refers to either the front or the back of the stick. So if you see a dual rank, they're also often called dual-sided SIMMs, where it's basically, I mean, they literally have chips on both sides of the stick itself. Those are accessed through these RAS. I don't know if you're supposed to say RAS or RAS, but those lines are used to select which rank and which slot you're actually addressing. That gives you 4 additional bits of addressability, so that's 28 bits total, and 2 to the 28th is 256 megabytes, which, when you break that down, that's the maximum that this system will take, or could take. But you got to divide that by 2 for the number of slots, so that ends up being 128 megabytes per stick maximum. So now let's talk about 72-pin SIMMs. They're really simple. They actually have 32 data lines going into each of the SIMMs. So when it reads or writes, it's read or writing 32 bits of data in one operation. So they're really, really quite simple. 30-pin SIMMs are a different story entirely. They're not much more complicated, but they are indeed different. So they have only 8 bits of data width. So you ask, how could you possibly do that? And this is a 486, right? So every operation could be, or read or write, up to 32 bits wide on the data bus. So that's why there are 4 of these separate 30-pin SIMMs on the board, and there have to be 4 in a 32-bit wide data bus, which, again, is a 386DX or a 486. If you were to actually run with a 64-bit processor, you would need 8 of these SIMMs for this same mechanism to work, but it would work. So that's how they make up the 32-bit wide bus, as you can see in my picture down below. So address lines 0 through 11, those are shared across all of the SIMMs, so you know which cell you're actually accessing, but it doesn't matter which chip you're actually accessing. What they actually do is they break up this data bus into 8 bits each and direct each of those to each of the SIMMs. So D, 0 through 7, goes to SIM 0. 24 through 31 bits on that operation go to SIM 3, and so on and so forth. So here's a complicated sheet that shows the bus timing. And really, when you look into it, it's not too bad. What it's actually showing you, each of these windows, if you've never seen one of these before, what it's showing you is that each of these is defining the minimum and maximum times that each of these operations has to run, so that you can use this to build up a system. But we're not going to worry about that. I just wanted to show you this RAS line and this CAS line and how they end up working. So this is the row select up here, and this is your CAS, this is your column select. So they both start high because these are, the pound sign means that they're active low, meaning 0 volts is when they go low, or, well, not 0 volts, but less than half is when they go low. So what ends up happening, or when they're triggered rather, activated. So both of these start high. You load, or the CPU loads the address onto the for the row into the address bus, and then you drive the RAS low. On that falling edge, that data is locked into the chip, and once it's latched, you then will load up the column, and then that's when you drive the column low. Not sure which is which. I didn't look it up and actually read it, but the when you drive that low, then the column is latched in, and because write enable is active low and it's high, that means it's a read operation. So the SIMM loads the data from that cell back onto the data bus, and it can be read back in. So there's your 31 bits in there, or 32 bits in the case of the 72-pin SIMM. And that's my last slide. So let's get back to our project. Installing memory in a system like this is you put them in place straight down like that, and then they snap in. And you have to do that times 4. And then I will put the original chip back in, the 72-pin. And there we go. Then I'm going to put that video card back in. I'm going to put it into the slot closest to the CPU, which is generally the fastest slot. Like I said, I like to brace these from underneath because those VLB slots are very, very tight as you press them in. There. The only thing left to do is boot it up and see if the new memory works. So I'm going to run this 3D Bench 1.0 for slower PCs, because I think this qualifies as a slower PC. So I'm going to run this and see what we do. This is with the S3 video card in it. We'll see what it gets for an overall performance. I'm guessing that number counting down is the number of seconds remaining. Well, that part seems zippy. Look at that. Wow, how pretty. There you go. This VGA system has a Superscape benchmark of 27 frames per second. Let's swap it out, put the Cirrus Logic card in there, and see how much slower it really is in this 3D graphics, I guess. It's 3D, but 3D graphics test. So now I'm going to run the same 3D Bench 1.0, but this time it's on the Cirrus Logic card. When I bought this system, it actually came with the Cirrus Logic card. So I didn't do any performance comparisons or anything like that before buying it. So It just came with it. And I just happen to have this other S3 Stealth 64 card laying around. I'll show you that one in a minute. While this here runs, and seems to be about the same speed, to be completely honest. Yeah, 26.3, but I swear when I was running Duke, it was definitely faster on the Stealth 64 card, and I'm not entirely certain why, but these show about the same in this benchmark anyway. Anyway, it should give us enough memory, because now we have 8 megabytes. Should give us enough memory to be able to play some Duke Nukem 3D, so let's give it a go. Yay, DOS 4 GW didn't kick us out, so we are off to the races. And we have some Duke Nukem. I think it's going to be a slideshow, though, still. This is a slow machine. So let's get in the menu. This is at 320 by 200 standard VGA resolution. And yeah, that's pretty slow, but that looks playable. So that's a little better than it was. Well, that's it for this episode of Infinite Hobby Loop. If you like what you saw, go ahead and subscribe so that you don't miss anything from the Beige Beauty series. See you next time.